Hello and welcome to Data Science for Ecologists in R. In the last video, we introduced some R functions to deal with linear models. Today, we will basically apply the same functions as last time, but we will consider a more complex example to get a feeling for what relationships can be represented with the linear model. More specifically, we will look at a dataset that contains the height of a certain tree species and various factors that have an influence on the height. Once again, we start by loading the car package and our dataset. By inspecting the data, we can see that there are 252 observations of 4 variables. We have the height of the tree in centimeters, the age in years, the average suntime a tree received per day in hours, and a treatment variable that indicates which experimental condition the tree belongs to. As you can see, the treatment variable is an integer at the moment, so we have to recode it into a factor. Furthermore, we center the suntime variable by subtracting its mean. You will soon see that this makes interpretation easier. To get an overview of the data, we now run the summary command. For example, the mean suntime is now 0 because we centered it. Furthermore, there are 3 treatment groups with 84 observations each. Given these variables, we could think of many different models for the height of trees. To keep it simple here, let's just assume that we have some evidence that the model specified by this formula right here is a good candidate. I guess it is not immediately clear what linear model this formula stands for, so let's talk about this in a little more detail. In general, I recommend you to read the documentation of the LM function to learn more about formulas. But for this concrete example, I will show you how to translate the formula to the corresponding linear model. The left side of the formula is of course the outcome variable. And we also know that an intercept is added automatically, even though it is not specified in the formula. Then the effect of the variable year is added. However, the effect of the variable year is not expected to be the same in all treatment groups. That's why an interaction term between year and treatment is included in the formula by writing year:treatment. In the linear model, this interaction is represented by using the dummy variables treatment 2 and treatment 3. Let's just quickly verify that this model can capture different growth rates in all 3 treatments. If a tree is in treatment 1, the dummy variables treatment 2 and treatment 3 are both 0. By simplifying the expression, we can see that beta 1 reflects the growth rate in treatment 1. If a tree is in treatment 2, the dummy variable treatment 2 is 1. And by simplifying the expression, we can see that beta 2 reflects the difference in growth rate between treatment 1 and treatment 2. Lastly, if a tree is from treatment 3, the dummy variable treatment 3 will be 1. And by simplifying the expression, we find that beta 3 reflects the difference in growth rate between treatment 1 and treatment 3. In summary, the interaction terms allow the model to capture different growth rates in all 3 treatments, with the parameter beta 1, beta 2, and beta 3. Let's now come to the last part in the formula, which specifies an interaction effect between the variables year and suntime. We can represent this interaction effect by including the product between suntime and year in the model. Let's see how this interaction term can be interpreted. For a tree from treatment 1 that received an average amount of suntime per day, the variables treatment 2, treatment 3, and suntime will all be 0. Remember that we centered the suntime variable such that the value of 0 stands for an average amount of suntime. By simplifying the expression, we see that we can refine the interpretation of beta 1. It is the growth rate for a tree in treatment 1 with an average amount of suntime per day. If a tree received, for example, half an hour more than the average suntime per day, the variable suntime is 0.5. And by simplifying the expression, we see that the parameter beta 4 modifies the growth rate per year according to the suntime. Alright, I hope that makes it a little clearer what model we have specified and how it can be interpreted. So let's go back to R. After we fit the model, we can use the same commands as in the last video to make inferences about the model parameters. We can see that trees from treatment 1, which received an average amount of suntime per day, are estimated to grow roughly 27 centimeters per year. Trees in treatment 2 are estimated to grow roughly 3 centimeters faster per year than trees from treatment 1. On the other hand, there doesn't seem to be any notable difference between the growth rate in treatment 1 and treatment 3, as indicated by the relatively high p-value. Lastly, the average suntime per day has a positive effect on growth rate, as should be expected. Each hour suntime is estimated to lead to roughly 4 centimeters additional growth per year. But as you already know, these are only the specific estimates for our data, so we shouldn't focus too much on them. Rather, we should use the conf_int function to obtain a range of parameter values under which the observed estimates are not too unlikely. Finally, we can also use the linear hypothesis function to obtain p-values for hypotheses that are not included in the summary function. In the last video, we looked at hypotheses for single parameters, but we can also consider hypotheses that include multiple parameters. For example, we might be interested in the hypothesis that trees from treatment 2 and treatment 3 grow equally fast. In statistical terms, this would mean that these two parameters for the interaction effect are the same for both treatments. In this case, we would expect 0 if we subtract one parameter from the other. This is specified in the arguments of the linear hypothesis function. 1 times the parameter from treatment 2 minus 1 times the parameter from treatment 3 equals 0. The p-value for this hypothesis is very low, which suggests that the observed estimates are very unlikely under this hypothesis. Consequently, our data suggests that trees in treatment 2 and 3 do not grow equally fast, which seems logical given that the two parameter estimates are quite different from each other. Alright, with this I would like to conclude this video. I understand that there was a lot of content today, so don't worry if you didn't understand everything right away. Nevertheless, I hope that I shed some light on what can be done with the linear model. One aspect that we completely neglected so far is checking the assumptions of the linear model. So in the remaining part of this module, this very important topic will be covered. See you soon.